let's continue with our discussion about the different gas laws. Again, the Boyle's law tells us the relationship between pressure and volume. Charles' law, volume and temperature. Gay-Lussac's law about pressure and temperature. We can summarize the relationship between these variables into these equations. Again, Boyle's law about pressure and volume. Charles' law about volume and temperature. Gay-Lussac's law about pressure and temperature. Now we can combine this law and form the combined gas law. So we have this equation, PV over T is equal to constant K. Now we can have this equation. This is the combined gas law. We have P1 times V1 over T1 is equal to P2 times V2 over T2. Or is equal to P1 times V1 times T2 is equal to P2 times V2 times T1. This is the combined gas law. Again, this just combined the volume, the pressure, volume, and temperature relationship. Now again, we have this formula. Just remember this one. P1 times V1 times T2 is equal to P2 times V2 times T1. We can use this formula over here. P1 times V1 times T2 is equal to P2 times V2 times T1. Now here, a gas filled with balloon, a volume of 2.5 liters at 1.2 atm and 25 degrees Celsius is allowed to rise, blah blah blah. So these are the initial volume, pressure, and temperature. Now this one is the final. This is the final temperature, then the final pressure. We're asked to calculate the final volume of the balloon. Okay, first we have P1, so the initial pressure is equal to 1.2 atmospheres times the initial volume is equal to 2.5 liters. 2.5 liters times the, again, we're looking for the final temperature is equal to negative 35 degrees Celsius. Now we're going to convert this one to Kelvin. That is negative 35 plus 273.15. So we have 238.15 Kelvin is equal to the final pressure. The final pressure is equal to 0.39 atmospheres. We don't know the final volume, so we will place here V2 for now. Then the initial temperature is equal to 25 degrees Celsius. Again, convert this one to Kelvin. That is 25 plus 273.15. To convert this to Kelvin, we have 298.15. 298.15. Now we can divide both sides by this number, 0.39 atm times 298.15 Kelvin. So cancel. What's left here is the V2 again. We're also going to divide this one, 0.39 atm times 298.15 Kelvin, and for that I'll give the rest to you to solve this one. So just multiply, then you divide. Okay, that's how you get the final volume for this one. That's the combined gas law. We have P1 times V1 times T2 is equal to P2 times V2 times T1. Okay, that's the combined gas law. It just combined the Boyle's law, Charles' law, then Gay-Lussac's law. Okay, next we have the, okay, let's discuss about, again, we have for the pressure, volume, we have the Boyle's law. Volume, temperature, we have the Charles' law. Pressure and temperature, we have the Gay-Lussac's law. Again, we can combine this one to form the combined gas law. Now let's add one variable here about the amount or number of gas particles of gases. Now here, or the number of moles, let's discuss the relationship between the number of moles and the volume of gases. So obviously pag of course this counts the number of particles. So obviously pag mas marami yung particles, obviously mas malaki yung volume, right? So this is about the Avogadro's law. The volume of a gas is directly proportional to the number of moles of gas present. So we can have this formula over here. V1 times N2 is equal to V2 times N1. Again, this means the number of moles. That's the letter we use to represent the number of moles. We have, again, V1 times N2 is equal to V2 times N1. Okay, what do you think will happen? Here we have the number of moles increased from 1 mole to 2 moles by a factor of 2. What do you think will happen to the volume? The same thing, increased by 2. That's 2 liters. Then from 1 mole to 3 moles by a factor of 3. Volume by a factor of 3. This is also 3 liters. Okay, again, that's the relationship between the volume and then the number of moles that's stated by the Avogadro's law. Again, we have V1 is N2 is equal to V2 times N1. A balloon containing 1.47 moles of gas has a volume of 0.783 liters. If 3.55 moles of gas are added into the balloon without changing the temperature and pressure, what will be the new volume of the balloon? Again, this is the initial number of moles, initial volume. This is the final volume, and we're looking for the new volume of the balloon, or the final volume. Our initial volume here is equal to 0.783 liters times the final number of moles, that's 3.55 moles, is equal to V2. The V2, we're looking for the new volume, times N1. N1 is equal to the initial number of moles is equal to 1.47 moles. Then again, we're looking for V2. Divide both sides by 1.47 moles. 1.47 moles. What's left here is this one, 0. We have, sorry, 0.783 times 3.55 divided by 1.47. We have 1.89. 1.89 liters. That's the new volume on this problem. That's the Avogadro's law. Now we can combine the Boyle's law, Charles' law, Gay-Lussac's law, then the Avogadro's law into one equation or one law. That's the ideal gas law. So again, we have this formula for Boyle's law, Charles' law, Gay-Lussac's law, Avogadro's law. We can combine this all to form the ideal gas law. We have PV and RT. So this R here, this is the ideal gas constant. So that's another constant. But here, this is constant. So this will be constant na. So here, the R, or the ideal gas constant, is equal to 0.0821 atm times liter over mole times Kelvin. So for this, memorize this constant. You might need this in your ideal gas law problem. Okay, let's try to solve this one. How many moles of an ideal gas are there if the volume of the gas is 146 liters at 14 degrees Celsius and a pressure of 3.45 atm? Again, the formula for this, we have PV is equal to nRT. The pressure is equal to 3.45 atmospheres times the volume is equal to 146 liters. Then the number of moles is, we're looking for the number of moles. Then the R, again, this is always constant. We have 0.0821 atm times liter over moles times Kelvin times, what's the temperature here? That's 14 degrees Celsius. So the same thing, this must be converted to Kelvin. We have 14 degrees Celsius, that's 14 plus 273.15 to convert this one to Kelvin. 14 plus 273.15 is equal to 287.15. 287.15 Kelvin. Now we're looking for N, so divide both sides by these numbers. 0.0821 atm times liters, moles times Kelvin times 287.15 Kelvin. What's left here is the number of moles. Again, you also need to divide this one using these numbers: 0.0821 atm times liters moles, then 287.15 Kelvin. Now, if you actually solve this one later, you can cancel atm, makancel yung liters, and then where's the Kelvin here? This is moles times Kelvin, by the way. Moles times Kelvin. So makancel yung Kelvin. So what's left here is the number of moles. Okay, so that's the answer for this one. Just remember this formula for the ideal gas law, and don't forget about the ideal gas constant.